Applications of a piezo-photocatalytic thin film for enhanced degradation of organic pollutants and disinfection of wastewater. The focus of this research is on enhancing wastewater treatment using piezo-photocatalytic thin film technology. The research aims to develop a novel thin film material that has fluorine-doped tin oxide, barium titanate tin dioxide that combines photoelectric and photocatalytic properties. It investigates the film's ability to degrade organic pollutants and disinfect wastewater. Greetings everyone. Today I'll be discussing an innovative solution for cleaning polluted water. For the introduction, a special thin film that combines piezoelectric and photocatalytic properties was created. A thin film is a layer of material that's extremely thin, typically measured in nanometers. Think of it as a thin layer of paint on the wall. Just like how the paint changes a wall's appearance, that's exactly how it applies. This technology has potential for removing harmful pollutants and germs. For the problem statement, the current wastewater treatment technologies are unable to efficiently remove organic pollutants and bacterial contaminants, resulting in an inadequate water quality for human consumption and environmental sustainability, a high energy consumption and operational costs, limited scalability and effectiveness in the real-world applications. The challenges are that the existing photocatalytic materials have low efficiency and stability. Piezoelectric materials have unexplored potential for wastewater treatment. Integrating piezoelectric and photocatalytic properties in a single material remains a significant technological gap. The consequences of this is that we will have continued environmental pollution and high health risk, increased economic burdens and wastewater treatment facilities, and we will have limited access to clean water for communities worldwide.
And for the methodology that will be utilized for the disintegration of microorganisms in wastewater, we'll be looking at the chemicals that are utilized, the likes of your barium chloride dihydrate, titanium dioxide, sodium hydroxide pellet, PVDF, NMP, which is N-methyl pyrrolidone, tet-butyl alcohol, and p-benzoquinone, which is PBZQ, and the dyed sodium salts of ethylene diamine tetraacetic acid, which is EDTA, which was obtained from the Sigma Aldrich in South Africa. Okay, we will be looking at the methodology continued. The thin film consists of a conductive substrate called the fluorine-doped tin oxide, layered with a piezoelectric material, barium titanate, and a semiconductor tin oxide. This enhances photocatalytic properties. We then look at the photocatalysis mechanism. We recognize that when exposed to UV light or ultraviolet light, the tin oxide generates electron hole pairs. Now occurs a charge separation. Electrons on the hole, they migrate to the surface, participating in redox reactions. Pollutant dehydration, hydroxyl radicals are formed, decomposing the organic pollutant. Then the piezoelectric effect, it appears that if we apply mechanical stress on barium titanate, it generates electrical charges in response to the mechanical stress. So polarization, the electric dipoles align, creating an electric field, and an enhanced photocatalysis is aided. Okay, wastewater is passed during operational processes into a chamber. That wastewater contains organic pollutant. The chamber contains the piezo-photocatalytic thin film. Now, ultraviolet light irradiation. Ultraviolet light is applied to the thin film, generating electron hole pairs in the tin oxide layer. The photocatalytic reactions initiate producing hydroxyl radicals. Mechanical stress is applied to the barium titanate layer. Piezoelectric effect generates electric charges, enhancing charge separation. Then the pollutant degradation occurs due to the reaction of hydroxyl radicals with organic pollutants, which will degrade them. Enhanced photocatalytic efficiency is then aided due to the piezoelectric field. Then the treated wastewater flows out of the chamber and pollutant concentrations decrease, achieving water purification.
Next up, we're gonna discuss the structural morphology and elemental composition determination. FeSME was used to capture micrographs of BTO, SNO2, and BTO at 0.2% SNO2 composite to get their morphological structure. And the TEM images of BTO, SNO2, and BTO, SNO2 composites. The tiny particles observed on surface of BTO SNO2 composites are SNO2, confirming the loading of SNO2 nanoparticles on BTO surface. Next, we are going to discuss X-ray photoelectron spectroscopy. The barium 3D profile on the figure confirms the presence of barium, and the titanium 2P profile on the figure confirms the presence of Ti4+, and the SN3D profile on the figure confirms SN4+ presence. The key findings are that the heterojunction formation between barium titanate and tin dioxide indicated by higher binding energies. The shift in peak position suggests changes in electronic structure due to SNO2 loading.
The degradation of methyl orange in wastewater using piezo-photocatalytic thin films was investigated. The use of fluorine-doped tin oxide, barium titanate, tin dioxide, piezo-photocatalytic thin films significantly enhances the degradation of methyl orange. Under both light and mechanical stress, degradation efficiency increases from 80 to 90% compared to 40 to 50% with the photocatalysis alone. The reaction follows pseudo-first order kinetics, with the rate constant doubling under piezo-photocatalysis due to improved electron-hole separation and enhanced ROS generation. The films remain highly effective after 5 to 10 reuse cycles, and the degradation produces safe, non-toxic byproducts. This process shows superior performance compared to either photocatalysis or mechanical stress alone.
So in conclusion, the barium titanate at 0.2% silver dioxide heterojunction piezo-photocatalyst demonstrated significant potential for the degradation of a wide range of pollutants, including dyes, pharmaceuticals, and bacteria, making it a promising solution for wastewater treatment. This study highlights the efficiency of piezo-photocatalyst in reduction of electron-hole recombination, enhancing photocatalytic performance, and providing a stable, reusable thin film. The successful collaboration and finding support from various institutions contributed to the advance of this research, paving the way for further innovations in environmental remediation technologies. We thank you guys for listening to our presentation. May you please like, comment, share, and don't forget to press the bell notification below and subscribe to the channel.